more surprising result they're claiming. So this we understand now. Parametrization independence, right? Parametrization independence. If you have a vector force field, if you're going from here to there like this, but we don't change the path. Path is there. If you go faster, slower, go back and forth and going like this, the contribution, the work contribution coming from this force field, which is position dependent, is always the same, right? Because this creates free fall motion when one thing, if you're going like that, an opposite, something different from the free fall motion, it is because of the other sources of forces acting on that. So the work contribution from this one is always the same. But they're claiming they're out there some special vector field. If you go from here to there and even change the path, go different route, the work is the same. The line integral, calculate this along this path, C1, this along that path, C2, they are the same. There are vector fields out there had this weird property, and they're stating one example. What is that example here they're stating? Gradient vector field. Who remembers a gradient vector field? It starts with a scalar function, xyz, and there's a gradient vector field denoted like this. At that position xyz, what kind of vector is assigned there? X component being partial derivative of x, y component being partial with respect to y, z component being partial with respect to z. There is this point in there, xyz, and temperature is assigned, right? Temperature function assigned. What is the meaning of this thing? Yeah, this is a level curve. So if you walk along this path, the temperature is the same. This gradient vector is telling you, go this way. Then what's going to happen? You arrive to the next higher level as fast as you can. This is the direction to the higher level as fast as you can. If it is really longer, turns out, you will arrive there really quickly. If it is a short vector, that's the direction to arrive to higher level temperature, but it's going to take a long time. You have to go some distance. So that's the meaning of the gradient vector. So vector field is coming from this gradient vector. They have this amazing property. It doesn't matter how you go and how you go there. The work done by this thing is the same, right? Okay. So path independence makes sense? Even if you choose a different path, not different parameterization, the work doesn't change. Even harder to understand why this one's happening, right? The proof is just really simple algebraically, but it's, as you can see, it's hard to understand why such property holds. So that's more of a mathematical side, but this turns out to be very, very important physical meaning, and gives you some sort of conservation principle. So they named it different. Physicists named it differently. Look at it here. They're going to call a vector field, not necessarily gradient vector field, any vector field, has a property that if you go through a path C1 and path C2, then they're equal, right? Just like I described up there. And they before described the path independence, right? Exactly the same property is described in the last two sentences, right? And they name it different. Why would you do that? Because of the physical interpretation. Physicists realize that this is not just this property. There's amazing property interpretation to physics. They call it conservative. This vector field is conservative if it is a path independence. Same terminology, but it's coming from physics interpretation. So what is conserved? Energy is conserved, yes. Any path. The statement is like this. If I have this point A and point B, and how many paths are there to going from here to there? Yeah, infinitely many paths are there, right? For all these infinitely many different paths, this guy is always the same. Unbelievable property. Yeah. If that's happened, what is this vector field called? Conservative vector field. What does that conserve? It conserves potential energy minus kinetic energy. here at that point, potential energy minus kinetic energy is the same as potential energy minus kinetic energy. That's what's conserved. All right? So they named that, but for now, we're going to focus on the mathematical part. So these two things are the same thing. That's equivalence notation, mathematics. And they introduced the third interpretation. This is more mathematical side, so that we can use this method and that method to prove the same thing. So if it is conservative, then they're claiming that line integral over closed curve. What is a closed curve? You started here, do some crazy thing, get lost, and come back to the original position. That's closed curve, not starting in here and end up as somewhere else. So closed curve is starting and do all the crazy thing and come back in here. That's closed curve. They're claiming it's the same thing. Conservative is the same as the integral around every closed curve is a 0. Okay? So for example, if it is a closed curve, if it is a conservative, let's see why this one is going to be 0. So for example, if you go around like this, you can just choose an arbitrary point out there. Look at this curve like this. This is you usually go around like this. To the interior region, you go around counterclockwise, which is same orientation in xy plane. So they usually orient curve like this. Suppose it's a closed curve starting from here, ending up at there. And you can divide it into two things. There's a C1 in there. And this curve, the C2. Let me use two different paths in here. This one arrow is for the orientation of a C. A double arrow is orientation for C1. And this is a C2 orientation, like this one. So C1 is starting here and going there, right? C2 is starting here and going there. So if I omit this inside because it's always the same, C1 is equal to C2. That's the property of conservative, right? So if I subtract this one from both sides, is minus C1. That's going to be 0, is a C2. But the negative is the same as opposite direction, right? So this is the same as integral over C1 plus integral over negative C2, which is opposite direction, right? But what is opposite direction of a C2? Going like that. That's opposite direction of C2, right? So C1 plus opposite direction of C2 is the same as the original curve C. And that should be 0 because we're subtracting here. So that can be rearranged into, if you just go around one time, that's going to be 0. And you can argue backward as well. If every curve is the 0 like that, if you go around like this, go around like that, you can turn it around and turn it into one closed curve, because all the closed curve is 0. Every path is going to be the same. So you can argue in a different way. So it's equivalent notion, which is algebraically very simple. Again, is intuitively you have to think about a little bit. If it is conservative, path independence. Another neat formulation is you start and come back in here, and work done by that force is 0. It only depends on your location, right? 0 work is done if you started and come back in here. So that's a third interpretation. They're all the same. So they summarize it like this, and I also summarize it with more of the notation. Path independence, they just named it different, conservative, and we just explained that the line integral over all closed curve C is always 0, not just 1 or 2. Everything you try, you will end up at 0 in there. All three things are the same notion. So for example, if you look at this problem, they didn't give you any specific. They just want you to think about what was just introduced. Here's a conservative vector field. That's the key. If it is conservative vector field, it's path independence, and every closed curve integration is the same, right? Is a 0. So they gave you this value. Line integral of this one along the curve AOB. AOB here is A's here. Go to O and go to B. That value, path going from here, the integral value here is equal to 3.5. They didn't give you the vector field phi, but they only give you the value of the line integral. So AOB in that order of the vector field like this, line integral, what is this value? 3.5. Suppose that's given. Such as, here's the velocity and here's the, well, this is not the only source of the field, so we can't argue that. So you can't argue the kinetic field because it's not the total force here, right? Okay, that's that. And what is it? The second question here, to find the integral along the broken lines. They're saying ACB, so I'm going to use the blue one. A is here, right? Where's the C? C is there and B is there. So it's going around like this, like that. What is the answer? ACB? 3.5. Because? Yeah, starting at the same point, end at the same point is a different path. However you parameterize it, however you take the different path, they're all the same. It's 3.5. How about BDA? Yes, BDA is B is here. Let me use green one. B is there and D is there and A is there, right? So if you go ADB, that would be the same as that one, right? But it's going opposite way, BDA, so that must be negative, right? Opposite way. So BDA going around like that. Of this integral, dr is going to be negative 3.5. How about ACBDA? So ACBDA. This is going to be 0. That's right. All right? Piece of cake? That was just about the notion. So I want you to think about this problem. And here's a vector field given. And they're claiming this is not conservative, right? So I'm just only going to do the same thing. Just one vector field. They're claiming this is not conservative, right? Neither. So how can you show this not conservative? You have to find one loop. One closed curve. C such that this integral along that closed curve should be what kind of number? Not 0, but what kind of number? Non-zero number, right? Yeah, if it is non-zero number, if you discover that path, you found it. This is not conservative. If it is conservative, it's supposed to be 0 all the time, right? If it is closed curve. So to show it's not conservative, this is all you have to do. Go ahead and discover one curve such that this is non-zero. All right? So what are you going to do? How are you going to go out and find the curve? I guess it's hard, right? So I wouldn't put this type of question in the test. It's difficult to. There are better methods introduced later. So let me suggest that I tried it, just a circle, because you don't want to try square. Then you have to integrate 4 times, right? Use a nice one so that one formula is available. So I tried circle. Let's see what happened if I go around the circle, right? So tried circle. How do you parameterize circle? Right. So I use it, easy one. Y and sine theta. T. And Z put around. I think it didn't matter. So I just put the same location, Z equals 1. And if you integrate along that, and T varying from where to where? 0 to 2 pi. That will be the one circle around it. Fair enough? And let's calculate that. What is this? Y negative x 1 dot dr, and then parameterization 0 to 2 pi. Y is a sine t, right? X is a cosine t, like that, is a 1, dotted with the derivative of this one, right? Which is negative sine t, as a cosine t, and that's a 0, and this dt. That's how I calculate it, right? So what happened? Yeah, if you do that one is negative sine squared t, this one gives you negative cosine squared t, right? dt. But if you factor out negative, Something interesting happened. What is the sine squared plus cosine squared? Is 1 dt. So what do you get? Negative 2 pi. What does that mean? Negative 2 pi is a very well-known non-zero number. So you proved what? What did you prove? It's not conservative. But if you have to prove it conservative, how many closed curve do you have to try? Infinitely many. So don't try one curve and turn out to 0. Ta-da, I proved it's conservative. It's wrong, right? There are a lot more to check. So there better be a better method than this one. But this is the idea, principle. Define something. This is how things are defined. But actually to prove is a conservative, you better have a better tool than trying all the infinitely many loops and then passing on to your son. I tried 1,000,000 of them. You try next 1,000,000 and see if it is 0. Nothing like that, right? But there better be a better method, all right? And they introduce a better method in the remaining section, all right? But until that time, you have a wonderful Thanksgiving break, and remember to do the homework on Sunday night. Independence is exactly describing the property, and some obscure property. The terminology is this conservative physicist named exactly path independence like that, a connection with the energy conservation. But this is another description. If you integrate vector field over any closed field, right? The C has to be closed field. Start and doing crazy thing and come back to the starting position. It always turns out to be 0. That's all these three things are equivalent. Today we're going to look at the gradient vector field and actually understand a little bit more why the gradient vector field is actually conservative, path independence. This is very hard to understand, right? Why is it? So let's write this one down. Not an exercise, but you need to understand the structure of the statement. So somewhere in your note, write this one down and sink this one in. Theorem. Phi is a vector field and is a gradient vector field of f. F is called a scalar function. Your input is a position vector, but your output is a scalar. But this if you do this operation, gradient vector operation, then it becomes a vector field. Then they're claiming that phi is conservative. Was it easier to prove it's not conservative, right? You just find one loop that closed curve, the integral is not 0, and you prove that it doesn't work, right? To prove it is conservative, you have to try all the closed curve, which is impossible. So we're looking at a different way. Conservative, and that's one fact, but it's more detailed facts that if your vector field is gradient vector field, then this line integral over C, starting from A to B, not necessarily closed curve, you start here and B there, it can be the same. Something crazy like this. You arrive at there. And they're saying this value of line integral is a value of the scalar function at the terminal point minus the scalar function at an initial point. Okay? That's what it says. So if I go like this, and let me use a different color. If I go like that, this formula says the value of a line integral is scalar function at that value minus scalar function at that value, right? So it doesn't matter what crazy thing you did in between. All that matters is the value at the terminal point and the value at the beginning point, right? So this explains, if you believe this statement, it explains it's a conservative, right?
This would also work if you were to evaluate where those paths crossed, right?
Right, yeah, it doesn't matter. What if the A and B are the same? So if you started here and end up at exactly the same point by doing crazy thing like that, right? Then what is the value of FB and FA? That's the same point, right? So evaluate the scale function, it's a 0, right? So that's a third criterion. If all the closed curve, if you evaluate it as 0, that's the same as conservative, right? So this is a most general statement that takes care of a conservative in the path independent sense. Also, the integral over closed field being 0 is all explained by this formula. Make sense? All right. But it looks a lot like fundamental theorem of calculus, isn't it? f of b minus f of a, right? There's indeed the disguised shape of that. So I want you to write this one down. The function f of xy equals e to the xy sine x. There's that function there. I'm about to review the shape, the meaning of a gradient vector field. It's been a while. I played with a gradient vector field. Let me explain that. F of xy, does it look like a scalar function? Right? If I give you a point here, this tells you the scalar, temperature, density, and those things, right? And what are these things that I sketched? Level curves. So this is a collection of all the f of xy such that f of xy is fixed to this value c. If I move along, what is the rate of change of the temperature? 0, because temperature doesn't change, right? Temperature is always 0. And if I choose that point right there, there's a gradient vector field assigned in there. That is denoted like this. Is gradient vector field is a scalar function? No, it's a vector assigned to that. Anybody know how to sketch that vector? What is that vector supposed to be? Yeah, straight to the highest level. And especially the relationship between this level curve. Normal, perpendicular, that's right. There's a tangent line, right? Is either this direction or that direction, perpendicular. So which direction is it? To the higher level, right? So when is this long and when is this short? These are all actually equal level. This is a level. This is 0.3 higher level. This is a 0.3 higher level. And this is a 0.3 higher level, and so on. So is this vector going to be long or short? To this distance, the level change to get to that 0.3 is a far distance, right? So is that the level is increasing slowly or fast compared to here? If I move it, you can see you cross this many different levels, right? So is that fast increase here? Yes, it's a slow increase, right? Therefore, it should be shorter. And here, it's longer. But to the direction perpendicular to the current level and direction to the higher level, and this length is depending on how dense those levels are. This is a gradient vector field, right? Remember those? So if this is energy, this is how this flows towards that direction. So they put negative, so it's higher to the lower level flow is because this is going to a higher level. It's called potential energy. So let's do this problem, one thing at a time. There it is. This is our official exercise today, number 1. You already wrote that function down, but you can write down again. E to the xy times the sine of x, be a scalar function like a temperature function. C is going to be a curve parameterized by this curve, t to the 9th times the sine raised to 9th power, and this is inside is simply pi over 2 times t. It's funny that how it typesetted the pi over 2 times t in there. T is varying from 0 to 1. First task, compute the gradient vector. Second task, you have a vector field and integrate this one along that. We're going to do part A first and compare our answers. All right. For the a gradient vector field is the first component is the partial derivative of that scalar function. Second one in partial y. For the x part, I had to use the product rule because a product of two functions both involves x and x in there. So I had to use the product rule. So if you differentiate the y come out. The second part is with respect to y. So this is sine x is a relative constant, multiplicative factor. So that's x times e to the xy. Any question about part A? Now once you write this one down in here, hope you recognize, oh, that's a vector field, right? It's a vector, and each point x comma y, the vector is assigned. So here's a vector field phi. The second part is asking you to compute the line integral of this one along this path, right? As you can see, this is complicated, right? E to the xy and all that. So let's think about what to do about this one. Here's a vector field phi, and we're about to integrate this line integral. Anyone have an idea on what to do? Here's a multiple choice question. Are you going to actually put this one and do the usual line integral thing, or something else? Something else. What is that something else? No? Some theorem, that's right. But not Green's theorem. The theorem that I just showed you.
But it's in the next section.
Not the Green's theorem. The one that I just showed you, and then you copied it down. Right. You remember that? Go back to your note. The line integral of this one is equal to something, right? That looks a lot like fundamental theorem of calculus, right? Use that. Yes. FP minus FA is magic. FP minus FA. That's what that is. So go ahead and try that statement. Alright, was that okay? So I just put random pictures. It doesn't really look like this. But this theorem says the line integral of the vector field that you're looking at is simply the scalar function evaluated at the terminal point and initial point like that. So I wrote it like this. And so what is B and A? Here's a curve. A is the initial point. You plug in t equals 0. That's where the beginning is. P equals 0 is there. 0, comma 0, right? And that's why we have 0, comma 0. When t equals 1, if you plug in 1 there, is 1 to the 9th. And here's sine pi over 2. Then that's also 1. So it's 1, comma 1, right? All that matters is function, the value of the scalar function at that point, and not what happened in between, regardless of this path, the pass through. So, and here is the connection. This is the magic in here. This is equal to the difference of the value. If we evaluated 1, 1, here is a scalar function. 1, 1 there is e to the first, and sine 1, 0, 0, sine 0, 0. So that's just this value, right? If you actually integrate, there is a way to integrate this one with all the thing and all the thing going in there. You can imagine is quite complicated looking integral. The change of variable is available. It's very difficult to detect sometimes. Yes. Okay. Thank you. But this one's still true, but that had to be corrected. Yes. Yes.
So conservative vector fields?
What about it?
This theorem only conservative vector fields?
Yes, this gradient vector field is a conservative vector field. Yeah, it's a part of the statement there. So if your vector field is coming from the gradient vector field, right, then it is conservative.
That's the only one dealt with that's conservative so far?
It turns out to be so, but right now it is, maybe there is some other vector field that is not necessarily gradient vector field anything, but maybe it's still conservative, right? There's a question. It turns out that there's nothing like that. So if every conservative is actually the gradient vector field. So if you see this conservative phenomenon, energy conservation in the physics phenomenon, there is this mysterious function called potential function out there that realizes your vector field. So it becomes this very important object in mathematics. That's the potential theory. Yeah. It's the next level of Newton's idea of a force direction and pulling to a really sophisticated level of mathematics. Let's enter potentials, energy. All right. Any other comments? The exercise makes sense? Yes. All right. Here is another exercise. Could be a bit challenging, but let's try it. Exercise number 2. Suppose the vector field you're looking at is a gradient vector field, or just vaguely trying, right? So what kind of vector field are we looking at here? So if you have to relate this one to vector field, although there is no vector field, right? If you have to put this one into vector field context, what should be the x component and what should be the y component of the vector field? Xy here? No, y first here, right? And x there. Why is that? Because if there is a scalar function whose gradient with respect to x, here that's the x component, and that's y component being y. So if I can solve this problem, and this vector field becoming the gradient vector field, right? Make sense? All right. Think about it. If there is a function with respect to it, y as a constant, you integrate it, you end up at y. What could be that f of x? If it's the other way around, what could be that, right? So that was the exercise. Right. Intuitively, maybe you notice that, oh, xy does it, and here's a little bit more explanation, more thorough approach. If the derivative with respect to x is y, y is treated as a constant, right? If you integrate, and it's obviously y times x, think about you do the iterated integral. This is how you do it, right? If you have y in it, if you have integrate with respect to x, this is how you're going to enter, right? But the constant term, it might have some bunch of y in it, but there's no x in it. So if you differentiate this one, you know it's going to be 0, right? Because there's no x in it. This is one way to write it. The expression where there's no x in it, but only in terms of y. So if you differentiate that one, that's going to be 0 here, right? So you can check that all this thing is actually, this is a full answer, right? Make sense? So it must be in that shape. And this kind of must coincide with the other piece of information. So I differentiated this one with respect to y to compare that with the other one. I haven't used that one yet, right? So if you differentiate that one with respect to y, then I get, if you is x plus, this one has y in it, differentiated with respect to y is just one variable derivative, correct? Good? Yeah, so that expression must agree with this one here, right? So that's x. If you set these two things equal to each other, you conclude that phi prime of y is 0. What kind of one variable function whose derivative is 0 must be a constant function, right? That's calc 1. So you can write it in general like this. In this effort, when you differentiate this one with respect to x, and if you compare to what they gave you, if they are no possible, for example, instead of x, if I have y in it, right? Then it's going to be contradiction, right? And what's your conclusion? Your conclusion is that this vector field here is not a gradient vector field because it's not possible. You can easily, for example, if I switch the sign to negative, then if you try that, you won't be able to match all the information. And your conclusion? Not conservative, not a gradient vector field. Not a gradient vector field, that's a correct conclusion. But here it all worked, right? If you actually try that, you can see that. So it asks you to find a scalar function, so you can just put a 0 in there. But if he asks you to find all scalar function, they define everywhere, and that with the one description, right? Fair enough? Question? So why don't you answer that? Let's think about this exercise number 3. Let's think about this homework problem. You were asked to prove something is not conservative, right? How did you do that? Yeah, find one closed curve, right? And integrate it and show that number is non-zero. Then you prove it's conservative, not conservative. But you are here asked to prove it's conservative, right? Then how many closed curves do you have to test? Infinitely many. And you cannot do that, right? Then what option do you have? Until this morning, you did not have any option. You didn't know what to do, right? Now we learned something, so we know what to do here. What is the approach? But then you have to choose your closed loop, right? Closed curve. But then infinitely many things you have to try. That's right. Think about what we just did. Exercise number 2. That's the hint. Look at exercise number 2 and answer exercise number 3. Right? That's exercise 3. All right. Using that theorem, that you can actually handle this one for arbitrary curve and like this. If it's closed curve, the beginning and end point value must be the same, so it's always 0. If it is over always 0 for over all closed field, closed curve, that must be conservative. Yes. Any question? Good. Let's think about this problem. That's exercise number 4. Evaluate this integral inside, looks like a differential form, but at the beginning of today's class we interpret this as an integral of what? Integral of a vector field. Yeah. So this is a vector field problem. Think about what vector field this one is, right? And how you're going to calculate this when C is parameterized by this one that we encountered before. And for that one, integral seems difficult, so we use something else. Let me rewrite this a little bit bigger. Integral. Let's see. All right, how was it? That makes sense? Yeah, you realize, hey, we've been looking at y comma x a couple times. Now you realize, oh, that's a gradient vector field, right? So the line integral is simply the difference of the value at the beginning and value of the scalar function called potential function. So if you have a vector field, you figure out what the scalar function, this is called the potential function for the vector field phi. Book also calls this an antiderivative, but potential function is a more standard term. I realize that this theorem that you were using here has an official name too. It's called fundamental theorem of line integrals, right? So rather than just saying about a theorem, we're going to refer to this one now, fundamental theorem of line integrals, and we can calculate this like this. It's a lot like the nature of a, difference of the kinetic energy versus that. It's of that nature, right? At the beginning, entrance velocity and terminal velocity determines everything. It doesn't matter what really happened in between, right? All right. So we'll stop here. We'll continue more of these tomorrow. And there were 4 problems and total score out of 8.